Hi there. So today I want to talk to you about some more surface physics. Specifically, I'd like to talk to you about bubbles and nanobubbles. So before I start with that, I have to explain why it's so amazing that we can even have nanobubbles in the first place. And to do that, I need to explain about Laplace pressure. The Laplace pressure is the pressure difference between the inside and the outside of a bubble. And the pressure difference is caused by the surface tension at the interface of the liquid and the gas. And it's described by the Young-Laplace equation, which is the delta P, which is the difference between the inside and the outside of the pressure of the bubble. So it's the excess pressure, if you will. It's equal to 2 times gamma, which is your surface tension, divided by R, which is the radius of curvature of your bubble. So you can see here that this excess pressure, what I mean by excess pressure, is of course you have the vapor pressure of the air inside of the bubble, and that's pushing outwards on the bubble. And then you have the ambient pressure, say 1 atmosphere or whatever it happens to be, pushing in on the bubble. And then you have the surface tension, which is creating a force that acts kind of inwards, okay? And so that one is indicated here with the little blue arrows, all right? So that's your excess pressure or your Laplace pressure. Now, if you plug into this equation and figure out what that excess pressure has to be, you can see that it changes with the radius of the bubble. So if you look at it, if you have a bubble diameter of about 1 millimeter or 1,000 micrometers, and you use the surface tension of water, which is 72 millinewtons per meter at 25 degrees C, then you can calculate what these values are. So if you calculate it, you get 288 pascals, which is 0.003 atmospheres for a 1 millimeter bubble, which isn't very much at all. If you go to a bubble which has a diameter of 3 micrometers, then you get 96,000 pascals, or about 0.95 atmospheres. So that's an excess pressure of roughly an atmosphere. And now if you take that diameter down to 0.3 micrometers, you get another factor of 10 there, okay, for 960,000 pascal, or 9.5 or so atmospheres. So a 1 millimeter bubble has a negligible extra pressure. Yet for a 3 micrometer bubble, the bubble has an extra atmosphere inside as opposed to outside. And when the bubble is only several hundred nanometers, the pressure inside can be multiple atmospheres, okay? So for that reason, everyone assumed for a very long time that nanobubbles couldn't exist for very long. The idea was their internal pressures would just get too high and they would either pop or be forced to expand in size really rapidly and be a bigger bubble, or they would just sort of dissolve in the solution and go away for whatever reason. So imagine everyone's surprise when in 1994 the first nanobubbles were actually detected. And in 2001, this group, Terrell and Attard, they actually published a tapping mode AFM images of nanobubbles, nanoscale bubbles, on hydrophobic surfaces. So the bubbles were actually being imaged here. And they found that when they switched to the contact mode AFM, when they actually just pushed down, the bubbles went away. They either moved them out of the way or they popped them. They weren't really sure. But that when they switched back to tapping mode and just gently tapped the surface, within 10 or 20 minutes or so, the bubbles actually reformed or moved back into the imaging window. Now these bubbles had heights of only about 30 nanometers, and they had areas of about 5,000 square nanometers. So they were kind of big flat bubbles that kind of just came up off the surface a little ways. Now in these images you see here, the top image is a phase image and all the others are height images, and so you can see the little bubbles being formed. These images are 1 micrometer on a side, so all the bubbles that you see here are nanoscale bubbles. Now, it gets a little bit better than that. They actually even saw bulk nanobubbles using cryo-electron microscopy. And what they did was they generated a chemical reaction between 2 TEM grids, okay? And then they froze it in place so that you could see the bubbles being formed. So these are electron microscopy images of frozen bubbles from a chemical reaction. And these bubbles are made of nitrogen. So you can see here that the radii of the bubbles are about 100 nanometers or 200 nanometers in diameter. And they're little tiny bubbles that have just been generated there. So nanobubbles exist. right? It's been proven, it's been shown. It's been shown in a lot of other papers that not only can nanobubbles exist, but they're actually pretty stable sometimes, okay? So if they're within a certain size regime, nanobubbles can not only exist for a fraction fleeting moment of time, but they can stay and be stable for weeks. So why, right? Well, there have been a lot of different postulates put out, but the most likely reason it looks like right now, or among the top reasons, is that the gas-liquid interface actually has a charge to it. And that charge introduces an opposing force to the surface tension. And I'm quoting Chaplin here. It's been shown that one surface ion to every 250 surface water molecules would stabilize a 100 nanometer diameter bubble. So how do you stabilize something that's unstable? You add in another force. And that force here is the surface charge. Now, the outward pressure due to the surface charge, according to Chaplin, should be phi squared over 2d epsilon naught, where phi is the surface charge density in coulombs per square meter, and d is the relative dielectric constant, which is assumed here to be roughly 1, and epsilon naught is the permittivity of free space, 8.854 times 10 to the minus 12 coulomb squared per newton meter squared. Okay, so those are the values in that equation. Now, if you assume that the Laplace pressure is balanced by that outward pressure from the surface charge, then you can set those two equations equal to one another. And then you can solve for a new reduced surface tension as a function of the surface charge density. So see here, it starts at the surface tension of water, 72 millinewtons per meter, and then it drops down from there as your surface charge goes more negative, okay? And it has been shown that these are negatively charged bubbles on the surface. Well, you might be saying, great, nanobubbles, nanoscience, nanotechnology, why do we care about nanobubbles, right? Well, it turns out they're good for a whole bunch of different reasons. One of the more recent papers is that Pennsylvania State researchers actually used a laser to create bubbles by heating water on a gold surface, and then they used the bubbles that they had created as a lens. Okay, so what they did was they used it to, you can see here without a bubble, and then this is an image, a lab image of the light beam that they're taking here, and you can see that it's being focused all over this grid. The grid is there for scale and also to help focus it later. Okay, so there's that image. And then with the bubble, you can see that they actually altered, they used the nanobubble as a lens and actually altered the path and size of the light beam. And so you can see that here. Here's a bubble, there's a bubble, and a bubble. And by adding these bubbles in a controlled way, by changing the power of the laser that they use to create the bubble and the position of the laser, they can deflect that beam of light using the nanobubble as a lens. So here's kind of a little schematic of their apparatus. They have a beam coming in, they create a bubble, there's the grating, the incident light, and simply by moving the laser or adjusting the laser's power, they can change how the bubble will deflect the light beam, either as a concentrated beam at a specific target or a dispersed wave, and changing the liquid also affects how the light beam will refract. And they say a nanoscale light beam modulated by short electromagnetic waves, which is known as the surface plasmon polariton, labeled SPP beam in the image, enters the bubble lens, officially known as the reconfigurable plasmofluidic lens, right? I like nanobubble better, but okay. And the bubble controls the light waves while the grating provides further focus. So they're using nanobubbles as lenses. Other work, believe it or not, people are trying to use nanobubbles for cancer treatments, or at least part of an approach, a suite of techniques, if you will, that are being used to sort of blast cancer away. Okay, so this has been done in mice and in a paper in Nature Medicine. And what they've done is they have these gold nanoparticles, and they tag the gold nanoparticles. They put compounds on the outside of the gold nanoparticles that target cancer cells. They move preferentially and stay preferentially in cancerous cells. And then what happens is they blast the nanoparticles themselves with a laser pulse they know will excite that gold nanoparticle. And then that creates a PNB, or a plasmonic nanobubble, okay, PNB for short. And then the explosion of that little nanobubble, the creation of the nanobubble, mechanically destroys the cancer cells by basically exploding them. And that's part of a suite. Like I said here, they have a little explosion, which is due to the plasmonic nanobubble. They also have a drug that they've used within the nanocluster, and when the laser hits it, the drug is released. And then they also hit it with X-rays that are known to be targeted to help excite with the gold clusters. So local X-rays, a local laser pulse, a drug nanocarrier, which is systemic, and a gold nanoparticle, which is systemic. Okay, so all killing cancer cells. And they have images here of the mice before and after they've been treated. So you see it's got 2 tumors here. Okay, they gave it 2 tumors. And then they labeled post-treatment the different tumors S and Q. Okay, S is the tumor that received the regular treatment, and Q is the site that received their new nanobubble treatment. And you can see the tumor's all gone. Okay. And finally, there were multiple uses for these nanobubbles that I could find in the literature. But finally, the one I would like to end with is water treatment. So the idea is to use these nanobubbles to treat the water and then avoid the use or maybe cut back on the use of some of the hazardous chemicals that they use to treat that water. So you can create nanobubbles in wastewater by cavitating it. And you can do that by sonication, introducing sound waves, or simply flowing the water rapidly, making the water flow and creating bubbles. And those bubbles can be micro or nano-sized. Well, the idea is that when the bubbles actually collapse, they form little hot spots. The temperature goes up within those spots. And that causes, the high temperatures cause the water molecule to break apart, and it generates free radicals, specifically hydroxyl radicals. And then those free radicals are known to be pretty effective at degrading organic pollutants and disinfecting the wastewater without the use of harsh chemicals. So that's the idea. So nanobubbles, they exist. We found that out in 1994. And we can use them in a variety of ways and diagnose their existence using the microscopies, which we've talked about, and also dynamic light scattering and some other techniques to figure out the bubbles and their size within the material. All right, well, I hope you enjoyed that, and I'll see you next time.